Hey guys, how's it going? And today we're going to be checking out net ionic equations and balancing them. So before we get into things, make sure if you guys need to know any information on science in the future or now, make sure to click the subscribe button down below if this video helps you out at all. So let's go ahead and jump on into things with our solubility rules. Before doing anything with net ionic equations, you need to know your solubility rules because that basically dictates how the entire thing comes out. That's how you're going to be able to cancel out your ions, your spectator ions, etc., which I'm going to show you guys here in just a minute. So what we have here, all nitrates are soluble, all acetates are soluble, etc. You're going to need to know all of this with the exception of maybe the sulfurs you might not get tested over, but it is still a good thing to know. So just know these, and if you would like to find these, all you need to go to is the Google search, and all you're going to do is type in solubility rules, and you're going to click on the images tab, and this image, along with many others that have your solubility rules all over them, is going to be there. So you guys can just go ahead, find that, click on it, and you should be able to get a nice nifty photo like this. I always use something like this when trying to remember and go over my solubility rules. Really helps out, especially when you're doing homework and stuff, but you need to have this memorized for testing purposes. So other than that, we have a lot of other example questions down here that you go ahead and pause the video and look at later on. However, right now we're going to go up to the top where I have some example questions that I'm going to work out with you guys. So first of all, we're going to block out that answer that's still out over there. Okay, so what do we have here? We have sodium chloride with an addition of lead nitrate goes to lead chloride plus sodium nitrate. So what is the first thing that we should do with a net ionic equation when working it? You need to write out your full equation and balance it. Okay, luckily they've done that for us here, so we don't need to waste our time doing that. However, if you haven't mastered that yet, you need to master that before doing this. And it's not hard. All you have to do is balance it, make sure everything on the left side is on the right side, following the conversion of mass. Well, yeah. Anyway, conservation of mass law. Anyways, let's go ahead and get into the gist of this with the net ionic equation. So, NaCl. What is important about that? Well, if you'll take a look at the solubility rules, which I'm not about to scroll down to, all sodium and chlorides break apart. Okay, so we know that's going to break apart. That's going to be our little annotation for that molecule breaking apart in reaction. Okay, all nitrates break apart no matter what, they all do, so that's good to know. And so what do we have here? We have PbCl2. Chlorides break apart, don't they? Well, most of them do. However, Pb plus 2 is an exception, and we're going to have a precipitant of, as you can see, a solid right there. All solids are always present at the end of solutions. So no matter what, if it follows the solubility rule or not, if it is solid in the end equation and it's written there for you, it's in there. So it's in there. Don't think too much about it. It's in there. It needs to be in your balanced net ionic equation. And then we have NaNO3. Nitrates and sodiums all break apart. Sodium is part of the group 1A metals. They always break apart. So that breaks apart. Ta-da! So now we can get to balancing now that we know what's going to be at the end of our solution, what we need to get to. We need to get to PbCl2. And what makes the PbCl2? Well, we can come over here. We have lead going into PbCl2. We have chloride going into PbCl2. That makes sense, doesn't it? Yes. So what doesn't go into that are these other molecules that have split apart in this solution during the reaction, and now they are just sitting around floating, having a happy old day. Well, those are called spectator ions, and when you're writing your net ionic equation, you go ahead and cancel those out. If you're writing your total ionic equation, you would just leave them. However, we're not doing that. We're writing our net ionic equation. So what you're going to do is you're going to go ahead and you're going to cross these ones that are going to cancel out. They're going to cancel because when they were to make a actual molecule at the end of the reaction, let's say that sodium and nitrate paired together at the end of the reaction like they have it written here, well, they would actually just break right back apart because of your solubility rules in an aqueous solution. Remember, this is in like water or something, which is not written into your equation. They would just break apart and they would just be floating around as normal Na plus and NO3 minus. And so the gist of it is you don't need to write those because they aren't having any significant factors into your equation. So don't worry about those. They have canceled out now, and all you're left with is Cl minus, and your Pb plus 2, plus your Pb plus 2, goes to Pb, Cl2. So there you have it. There's your first equation done. But what have we not done yet that you might be noticing? Well, as you can see, lead here has a plus 2, which means that it has 2 electrons up for grabs that it can be taken away from to fulfill its octet and make it a happy little neutral atom, blah, blah, blah. Anyways, chlorine has a -1 charge, which means that lead can take 2 chlorine atoms attached to it simultaneously. However, on the left side of our equation, we only have 1 chlorine. So before you finish your equations, guys, you got to make sure that they're balanced. So we actually need a big old number 2 in front of that chlorine, because here's our subscript over here of a 2Cl, but we only have 1 over there. So we need to add 1 more chlorine. So moving on to the next answer, we will go ahead and just check our answer on that one really quick for you guys. As you can see, there's the entire question worked out for you, and here is your answer right down here at the bottom. So hope that, guys, helps you. We're going to go ahead and jump on over to our second question now. So we have sodium carbonate with iron chloride goes to Fe, iron carbonate, plus NaCl. All right. Thank you again for having our equations written out. That's wonderful. Let's go ahead and go really quickly and go check out our solubility rules on carbonate. CO3 minus 2, there he is right here. All carbonates and phosphates are insoluble except for those of Na, K, and ammonium. So sodium, potassium, and ammonium. What does that mean? Anything with CO3 minus 2 attached to the back of the atom molecule will dissociate when in solution, or will not dissociate when in solution, unless it has an Na, a K+, or an NH4+ attached to it. Then it will break apart into its ions, but only in those very limited circumstances. Okay, so knowing that, let's come up here to the front. What is this carbonate attached to? It's attached to sodium. So what does that mean? Breaks apart. All right, what do we have here? All chlorine, chloride, bromides, and iodides break apart. Let's go ahead and go back down there and check on that one. All chlorides, bromides, and iodides break apart except for those of Ag+, Pb+, and Hg+2. So that is silver, lead, and mercury. All those break apart except for those 3. So all of them break apart except for those 3. What is in front of this chlorine? Not a silver, lead, or mercury. So what does that mean? Breaks apart, aqueous solution. What do we have here? Iron carbonate. That is not one of the 3 soluble carbonates that we had at the beginning of the video, or this question. So that means that this does not break apart. And what do we have here? We have NaCl. Good old sodium chloride. It's going to show up all the time. What does that mean? In an aqueous solution, all bromides, chlorides, and iodides break apart, and all group 1A salts break apart. Hydrogen is not included in that. Anyways, that means they break apart. So what do we have here now? What is going to be breaking apart and what's going to be staying together? Well, we know that we have iron carbonate as our end molecule. That's our precipitant in the solution. So we need to have the ions that make iron carbonate. And then we have these other ones that aren't going to be related. So what do we have that's going to break apart and just sit in the solution? Well, chloride is just going to be floating around. What else is going to be floating around? Sodium. Sodium's also going to be floating around. What are we left with? We are left with our Fe plus 2. If you're wondering how I can tell which variation of Fe it is, it's because Cl, we'll go ahead and erase those little markings I have on it for just a second. Cl is naturally a negatively 1 charged particle, and so since iron is holding 2 chlorines, that means that Fe must be plus 2 because the charge overall has to equal 0 in order for the molecule to be a happy little camper and be stable enough to exist. Okay, so what does this mean? Fe plus 2 is the ion when that molecule breaks apart. And let's see, same thing goes over here. Na is a plus 1 charged atom, so that means that carbonate must be a minus 2 molecule. CO3 minus 2 plus Fe plus 2 is going to go to FeCO3, and that's a solid. Make sure you write your solids down in there. I probably forgot to do that on your last one. They sometimes like you to have your little annotations down there. I honestly don't think it's that big of a deal, but sometimes they like to have those annotations down there. And so we can go ahead and we can check on that answer now. Da-da-da-da. CO3 minus 2 plus Fe plus 2 goes to FeCO3 solid precipitant. So there you go, guys. There's that. And so we can go ahead and do one more just before I go down there and just let you guys look at all of the equations and their answers. So what do we have here? So here we are on question number 3, and this one's going to be a little bit unique because we have hydroxide in the mix here. So as you can see, it's going to be a little bit different for that one. So what we can do here is, like I said before, you look at your equations and you see how they're going to work out. So what we have here is your Mg, your magnesium hydroxide, and your hydrochloric acid. Well, shocker, hydrochloric acid is a strong acid, which means it's always going to break apart. And then what do we have over here? We have MgCl2. All chlorines break apart except for a few, and magnesium is not one of those. And then we have H2O, which is a liquid here, which is different. It is not aqueous. H2O will not be breaking apart. So there you have that. And then we have our little special guest over here, magnesium hydroxide. So what are our hydroxide rules? All hydroxides are insoluble except for those of Na plus and K plus. And hydroxides of barium and calcium are slightly soluble, but don't worry, that's not the situation at the moment. However, so that would mean that this one doesn't break apart, right? Wrong. It actually does break apart in this scenario because of the way this equation works, with this type of equation ending up down there at the end with water as your end result. So what do we have going on here? So we have an H plus, which is going to be factored into this final thing over here that doesn't break apart, your water. So your H plus is going to be going into that water. And what else is going to be going into that water to make the water water? Well, this OH minus is also going to be going into it, and OH minus plus H plus makes H2O. There you have it. So what does that mean for this guy over here? Well, that means that he must break apart. So Mg plus 2, because the OH is minus 1, and so OH 2 means that it has to add 0. And also, another way that you can figure out that Mg is plus 2, if you didn't already just have it memorized, is that, as you can see, Mg is in this second column here. And so let's start with hydrogen. The column with hydrogen in, everything in the hydrogen column is plus 1, everything in the second column is plus 2. That's pretty simple and easy to remember, I feel like. So let's go ahead and mark out what's going to be canceled out in this situation. Well, we're going to be losing this magnesium, and we're going to be losing this magnesium, because they're just going to be spectator ions. They're going to be both plus 2 in solution. What else are we going to lose? We're going to lose these chlorines. They're going to be sitting around spectating in solution. What a surprise. And so now we have OH minus plus H plus goes to 2H2O liquid. Very important that you remember the liquid part there. So that is about how you do that one. That's how your equations are typically going to look with the waters. Don't let the water ones stress you out. They're actually a lot more simple than they look. So let's go ahead and we can check our answer now that we know that. So we have 2OH plus 2H plus goes to 2H2O. And again, just make sure that you balance your equations, which I did not do at the end right there. Make sure you balance your equations to make sure that they all work out, because we did have 2H2O here, or we had 2OH there. We have 2H there. They can't just disappear. So make sure that you have the right amount. Of course, however, your final answer right here is OH minus plus H plus goes to H2O. So the reason for that being is that these are all 2, which means that you can divide the entire thing by 2 and you just have 1. So technically your balanced equation is this. However, because that's the amount of moles that you started with, however, and that's the amount of moles you can end with, however, when you reduce it like a fraction, you get ones in front of all of them. So, thank you guys for watching, or I'm going to go ahead and just scroll down and erase a bunch of the answers that I have hidden, and I'm just going to let you guys, you can look at them, and if you need, actually I'm not erasing any answers, you can just look at them right here. So here's a bunch more equations and examples, a little bit more complicated ones probably. Here's an acetate one down here that you're going to probably want to look at. Acetates are a little tricky sometimes, but remember, here are your solubility rules as well. I recommend looking that up. And so, without further ado, thank you guys for watching. I hope this helps you just a little bit with your net ionic equations, and if you need anything else, just go back or leave a comment down below. I might be able to help you. So, thank you guys for watching. I'll see you later.